So let me present you the team working on topic robust speaker recognition over varying channels. So maybe first let me introduce you the team. You can see that we have plenty of people in our team from many different sites, and actually those also few working with us distantly. Those are in that gray color. Some of them also coming for the workshop, at least to show up here for a few days, namely the people from SRI. And maybe let me start with saying a few words about SRE NIST evaluations, speaker recognition NIST evaluations. These are evaluations annually organized by National Institute of Standard and Technology. And the purpose of the evaluations is to provide some common paradigm for comparing technologies developed by different sites. And actually, all our team members participated in recent NIST evaluations. Actually, just 2 weeks back, we all met for NIST workshop in Montreal, and we all had chance to discuss our ideas and what we did for how we build our system for evaluations. And we see this JHU workshop as an opportunity to actually do some common post-evaluation work. Everybody in our team is full of ideas and willing to share the ideas, and we would like to actually combine the ideas and improve the techniques that were developed by individual sites, and we believe that we can actually advance the technology this way somehow. And thanks to the NIST evaluations, we have right now identified some of the current problems that we would like to address during this workshop, and we have actually well-defined setup and evaluation framework which will allow to measure the results of the workshop. We will see whether we have improved the technology or not, and I believe we will. And we have actually nice baseline system that we want to start from. I was showing you similar picture during the summer school. Those were results from 2006 NIST workshop, and now these are similar results from 2008 workshop. And again, I'm showing you blind death curve that are, well, who doesn't know how to interpret that, just closer the death curve is to the origin of this graph, the better the system is. And this is just, there were several conditions during these evaluations, and this is just for the telephone condition that we at least want to start with. And well, again, I'm not supposed to say who had the best system, who was second, and so on, but I can say these are the performances of all the system, and this was actually the BUT system for the telephone speech, so you can, again, figure out by yourself. And actually the systems of the other people from, those are not actually colored lines here, but all the team members are actually from sites that are the leading groups in speaker identification technology. So I think we have good baseline to start from, and we have good chance to improve the technology. Well, Patrick already said a few words about the largest challenge in, well, to practical use of speaker detection systems, and that is the channel and session variability. What we mean by session variability is anything that changes the speech. Our problem is that we have always only a small amount of speech to train our speaker models, and then we are supposed to recognize speaker from another recording, and the other recording can be recorded other different channel condition, meaning different microphone, different acoustic condition. The speaker can speak different language in those two recordings, and we have to deal with all these problems. Just to illustrate how serious the problem is this is again some result from 2008 NIST evaluations, and this shows performance for system. This is interview conditions, so there were some interview recordings for training and testing the system, and the interviews were recorded over different microphones, and the red line actually shows you the performance of the system if training and test segment was recorded always over the same microphone, and how much worse it gets if you consider different microphones for training and testing. Basically, you can see 3 times worse performance if you consider different microphones. And this is only the microphone difference. And of course, there are the other factors that degrade the performance. So maybe let me first show you what is the current way of dealing with the problem, basically what Patrick was talking about. And for simplicity, let's consider just 2-dimensional feature space. We are going to model the features using Gaussian mixture model, but in this simple case, just using single Gaussian model, actually. And the way we do speaker recognition, we take all the training data, we train some universal background model that's supposed to represent any speaker. Then we get a little bit of the test data, few frames of the test data. Well, usually we want to work with segments of about 2.5 minutes of speech. And we adapt actually the universal background model to the training data. And then we get another recording of the same speaker, possibly of the same speaker, but we can see that actually this data would maybe better fit to the universal model than to the target speaker model. So if we try to recognize the data, we would fail in this case. But say what we do right now, we will train another speaker model of using the other recorded under different channel conditions. And maybe we will take another recording and we will train other and other model, and we will get the whole continuum of models for the same speaker. We could do the same with different recordings of another speaker and another speaker. And now we would identify in this space 2 directions. One direction would be the direction of large intersession variability. So the direction of how the model changes for different sessions, even though that it's the same speaker, and direction with large speaker variability. Well, right here it's showing actually directions in feature space, because we are just dealing with single Gaussian model. But generally we would use not just single Gaussian model, but Gaussian mixture model, and we would be looking at the directions of the model parameters. So that would be potentially higher dimensional space, and we usually work with Gaussian mixture model with 2,000 Gaussians and 60 dimensional features. So there are hundreds of parameters of the model, and we are trying to search for such directions in those 100-dimensional space. Well, now once we identify the directions, and right now we would be looking just at the directions of high intersession variability, how we can use the fact that we have learned what is the direction. Now we have the target speaker model, we have the UBM, we get some test data to recognize, and if we try to recognize the test data using the target speaker model, we would fail. I mean, the decision boundary that says whether, if we were supposed to decide whether it's closer to UBM or whether it's closer to target model, here would be the decision boundary. We would recognize that it's probably the UBM, not the target model. So we would fail in this case. And how to solve the problem? Let's adapt both the UBM and the target model. Let's move them along the direction of the high intersession variability and move it to make it closer to the test data. So both the models are moved along the direction to well fit the test data. And now we see that the speaker model is actually much closer to the data, and we would do much better in this case. So this was the basic idea about compensating for channels. Currently, we are using more complicated probabilistic model that was actually proposed by Patrick Kenny, that we are happy to have in our team, and we hope that he will help us to improve that further. And I am not going into details of this probabilistic model. We could spend probably hours, and Patrick would be the right person to explain you all the details, so you can ask him. But the basic idea here is, maybe I will first return to the previous slide I was showing. We adapted something just in the direction of session variability. Now we can also consider the direction of large speaker variability. And as I said, we can have larger dimensional parameter space. So in this case, we have already 3 directions. Let's say that this is 3-dimensional parameter space, and we allow to adapt the model parameters, which would be, say, means of the Gaussians in this 3-dimensional parameter space. And in this 3-dimensional parameter space, we can identify some subspace, say 2-dimensional plane with high speaker variability, some 2-dimensional plane with high intersession variability. We can find the directions of the large speaker variability, large session variability. We can even identify how much variability is in those directions. And this actually defines some probabilistic model that can be fully trained in probabilistic way using EM algorithms and things that we know from machine learning and training the probabilistics model. And this is actually what we would like to start with. I'm again showing the same picture that I showed a while ago, which is showing the performance of our system. And this is actually the performance of the factor analysis system that we want to start with. Well, in our case, it was actually fusion of 3 systems, but if we looked at the performances of individual systems, just the one factor analysis system performed about the same. So you can see that the factor analysis framework is actually provides the state-of-the-art performance, and this is something that we would like to start with. Now, what we would like to do during this workshop? Well, the main thing is take the joint factor analysis framework and improve it somehow. And we have some idea how to do that. And the first thing that I was already presenting during the meeting the last fall was the discriminative training of a factor analysis system, and this is what I am mainly interested in. Then there are some other problems that were actually identified during the work on these NIST evaluations and that we would also like to address. So let me just go step by step through these individual things and say what the problems are and how we would like to solve those. So why I would start with discriminative training. Maybe I will spend more time on this because this is what I'm interested in, and I will shortly address the other things. So why the discriminative training? Actually, it proved to be successful for other tasks. For LRE, which is language identification NIST evaluations, there was us who started with, the Brno team who actually started with discriminatively training models for Gaussian mixture models. Well, people also used support vector machines and called it discriminative training. So in this case, those were discriminatively trained Gaussian mixture models using maximum mutual information criteria, and we actually got 50% relative improvement just compared to the conventionally ML trained models. And in 2007, if you look at the 6 best system in those evaluations, you could actually see that all of those use the discriminative training. So it really seems to be effective. So what is new about that for speaker recognition? Well, as I said, we typically have just small amount of enrollment data and small amount of test data, and the small amount of training data, this allows to use the standard discriminative training techniques as we use them for other tasks. We usually need plenty of training data to make it really effective. And we have to consider the problem with intersession variability. And actually also we have just recently, we got enough of training data, many speakers recorded over different channels that would allow us to train such discriminative model or discriminatively trained Gaussian mixture model, discriminatively trained models for speaker recognition. Maybe just again the demonstration what the problem is. Before I showed you that even for ML trained model or the adapted model, we would get the decision boundary wrong. But if we try to retrain such speaker model discriminatively, it actually tries to separate the speaker data from the general data, so it would even try to separate the red dot from the blue dots, and we would probably end up with model that looks like this, that the decision boundary is even more incorrect, and we would get the target speaker even farther from the data. So the standard way of discriminative training cannot be basically applied in this framework. We have to think of something else. And the strategy for the discriminative training would be to train only the parameters, the model parameters that are common for all the speakers. So by this, I mean discriminatively training the hyperplanes showing the large speaker and large session variability. And then we would be trying to identify the speaker models themselves in that constrained space and training, probably using the standard ML techniques or ML or map estimation in the discriminatively trained subspace to get the speaker model itself. And as I said, this is allow just the recent data collection and recently introduced approaches for considering the intersession compensation. And also, we have used discriminative training before successfully in speaker identification, and this is actually a linear logistic regression used for fusion of system. But this is just we are just discriminatively training some weights for different systems. So this is actually very, very simple thing, or very reduced version of the thing that we would like to do during the workshop, where we were just training few parameters, while right now we would like to train a lot of parameters, the hyperparameters that are common to all the speakers. Now the other thing that the problems that we actually identified during the NIST evaluations and that we would like to address also during the workshop. Support vector machines, which is another discriminative training technique, proved to be effective for speaker identification before. Usually, this is actually what also Elmar showed you. He used the GMM trained models and tried to do support vector regression where features were the trained GMM model. So this is what we do for speaker identification. We train generative models, which are usually GMMs, and use the model parameters as features for support vector machines. And that proved to be quite effective, at least comparable with the other technique used so far. But actually, now we have the factor analysis model. When I say factor analysis model, I mean the factor analysis model considering both the speaker subspace and channel subspace. Some of the people, or we use some simplification of factor analysis model before. So if I say factor analysis, I mean the full factor analysis model that provides the state-of-the-art performance. And this one actually provides higher quality model, or at least model that gives you better performance, but it seems to not work very well in the support vector machine framework, or seems to provide good features for support vector machine. So this is one problem that we would like to look at. Why is that? Can we make it working again? Can we then improve actually the performance again by combining the joint factor analysis and support vector machines? If that works, or possibly we have to search for some new kernel definitions to make it working. And if that works, then maybe we could apply similar ideas to recently proposed fast scoring techniques, dot product scoring techniques that actually Nico from Agnitio that we have in our team used, and also Jason from IBM, they used similar ideas. So we have the people that know how to do that, and now they should teach us how to use the same thing for joint factor analysis, and that would allow us to speed up especially the testing of our system, so it would be of practical importance. Another problem that we would like to look at are variational bias extensions of joint factor analysis model. Again, I'm not going into details. This is idea that again Patrick came with, that we could investigate this possibility. Variational bias methods allows to train complex probabilistic model. Right now we have to make some approximation and some incorrect assumptions with the joint factor analysis model so that it is actually feasible to train the model. And with variational bias approximation methods, we could actually make less of the incorrect assumptions and approximations and possibly improve the model this way. And also it should allow us to apply the joint factor analysis framework to diarization tasks that we didn't know how to use it so far. So Patrick again has some idea how to use it for these tasks. And another thing that we would like to look at is call it conditioned joint factor analysis models. Again, in this year NIST evaluations, for the best performing subsystem of SAI team was something that they called constraint model. They trained several subsystem, each trained on subset of speech segments where the subset of the speech segments always belong to some linguistically defined category. So one system was trained only on frames from representing certain subset of phonemes, or only on syllables starting with certain phoneme, or different constraints were applied. And at the end, they merged all these subsystems and got quite interesting performance. And again, applying full factor analysis modeling to such conditioned system is expected to provide some improvement, especially because joint factor analysis is very effective in situations where we have limited amount of data for training the models, and here if we train those subsystems on just subsets of training frames, then those are really trained on just small amount of data. So the joint factor analysis could help in this case. And there is a variety of model configuration that could be applied for such condition models. So I'm not going to enumerate them all, but you will probably see during the workshop that we have tried few different configuration and few different modification of the models, namely if mixture of joint factor analyzers would be one thing that we would like to look at. And also there is variety of information or different kind of information that on which the system can be conditioned, like phonemes, syllables, language spoken in the segment, some acoustic content. Even those constraint doesn't have to be even discrete, but can be continuous and things like that. So these are things that people in our team are interested in. So the conclusions, thanks to recent speaker identification NIST or speaker recognition NIST evaluation, we are ready to share the ideas. We have the state-of-the-art baseline system. We have identified few interesting problems that we would like to address during this workshop, and hopefully we will solve at least some of them and push the technology forward. That's it.
We have time for lots of questions, but we're not going to take not 5 minutes.
Now less people have questions.
Any questions?
What data will you be using for this?
The data that we use for NIST evaluation. So basically, we would like to evaluate on 2008 evaluation data mainly.
A bit more? I think not everybody will.
Okay, so these are recordings of many speakers under many different conditions. We would like to concentrate on telephone data. So the setup or the evaluation framework is set it up the way that you have actually many trials. So you have many pairs of training and test utterance. there is for the telephone data. I don't know how many was this year, but could like 30,000, probably even more this year. So you have 30,000 of example, always some training recording and test recording, and you are supposed to say whether the recording comes from the same speaker or not, and the recordings are recorded over different channel conditions, or even the speaker speaks different languages and can speak different languages in the training and test segment.
I had a question. So when you look at these 2, 3, 1% errors, right? I guess people have listened to them. Can you tell us what kind of errors these are? So the speakers that you misidentify, why do you misidentify?
Well, still probably mainly, at least on the figure that I showed at the beginning, all the errors were, or the difference in the performance was really just because of the difference in microphone. So really only the misleading information in the recording is the difference in microphone. So it better fit to the speech of some other speaker because he sounded over different microphone more like somebody else. But
I guess my question is, if you heard it or if I heard it, would we know that it's the same speaker? I guess it's the other way around. I guess there are two questions. One is you have equal errors, so you're also having as many false alarms at 3%. So the speakers you're misidentifying, is it because the microphone is the same now, or? I just want to know what's left.
I really didn't listen to much of the data, so I think that these questions are actually for all the people from our team. So.
I can say a little bit from listening to it. One of the things you find as you get your error rates lower is you rejecting speakers that aren't the same stays relatively constant. What you find happening is it's the target scores, it's the true trials that suddenly the mismatch in there causes them to have a lower score, and it starts sliding in. You can't tell them apart from the non-target scores. So basically, the target distribution starts sliding down. I think that's what Lucas was getting at. So it's not so much that you're confusing, that you just can't tell two people that are different apart. It's actually that you're having trouble identifying the same person each time. Now, in terms of whether humans can do that, there's very little experiments on humans doing this because we do it, but we tend to do it with a small set of speakers that we know. The last human experiments that were done were around 1999, and in that case they found that, not surprisingly, humans were better about disambiguating the channel differences. We can sort of push those aside. The machines, because they're statistically driven and going after capture of features and so forth, really have a hard time in pulling apart the two. That's why these techniques for dealing with channel compensation tends to be the best. There are some cases, though, I would say, that when you listen to them, not necessarily at the equal error rate, where it's really hard to tell the two people apart.
This is run as a detection experiment,
exactly.
Then. So, how do you get confusion? Well, you mean confusion?
No, there's target trials and there's non-target trials. So here's an utterance, here's another utterance. Are they the same or are they different is what you're asked.
Oh.
And when they're the same person, but enrolled in one microphone and tested on another, that degrades the score, and suddenly that score starts to get lower and starts to head down toward the scores that you might see when it's two different people talking. So that's the part that the systems have to try to do.
So you can listen to the false alarms.
You can listen. What do you mean?
Yeah. If you want to compare two talkers. If you want to examine confusions, if target A picks talker B, you can listen and see if you can tell if they're different.
It doesn't pick. It's a detection task.
Yeah.
So all you're saying is yes, no. I think they're the same, or I think
But
they're
if
different.
there's a yes and it's wrong,
You can listen.
you can listen.
You can listen to those true trials that are missed also.
So what you're saying is that a big contributor right now are false negatives, where you reject a matched speaker by saying, I think it's someone else.
Well, I
And
don't
you're
think it's the
saying
same
that-
person. Yeah.
Meaning it is the target speaker, but the
Yeah.
system thinks it's not. And the system thinks it's not because the channel is sufficiently different.
Yes.
And so that's why you think that this is the key problem to work.
Yes, that's been our evidence so far.
Any other question? All right, so
There's one more.
Oh, there you are.
Hi, Lukash. So I noticed your detection error trade-off curve. You had your system further up towards the front. Now, I don't know if JHU may have submitted one, but you may not have the range large enough in the bottom corner where JHU was actually sitting. So it's interesting. So another question: how many parameters, like with this discriminative training criteria, how many parameters do you expect to optimize?
Well, we thought actually we are interested in that with Nico mainly, and I thought actually to start with eigen voice system where you would have 300 eigen voice bases of the same dimensionality of the system, so 100,000 of parameters, and so it's 300 times say 200,000 of parameters, and we estimate all of these discriminatively. What we did for speech recognition, we usually start moving the parameters in some direction and look at whether the performance improve or not, and we stop the training at some point. This is something that Nico doesn't like. He usually likes to optimize fully for some objective function and do regularization, and so different possibilities how to deal with the problem. Also, we thought of possibly training first just few parameters, considering just one eigenvoice, they may be the most important with largest variability out of all the eigenvoices, and start retraining just the one parameters and see whether it helps us or not.
Any more?
I had one more. No, it's just a comment, but
Okay, that's
no
fine.
meaning for him to comment on. And that is that you seem to put a lot of stock in this joint factor analysis. Now, if I take a set of models and I say, these are my model parameters and this is how they might change with some underlying hyperparameters, whatever, underlying variables X, Y, Z, what span of channel changes are you going to model with this? Is it just linear convolutions or?
Yeah, that was actually...
There are, of course, channel variations which are not in the span of this. So what are you
Yeah, this is actually one of the problems that we were even discussing during the last planning meeting. The factor analysis model expects that the channel effects are actually, you can make the linear combination of some bases and add them to the super vector of speaker to model the channel changes, which may not be the case for all the channel variations. And there are other techniques that tries to deal with that. For example, for face recognition, you can imagine, well, this was the example that actually Patrick also mentioned, and there are people, the primes from working on the recognition of face recognition, basically, and they have problem with different poses. So you may have picture taken from one pose, and then you may take the picture of the same person from other pose, and of course you can't create somehow the picture of the same person from, or change the one picture to the other picture just by linear combination of some other pictures of some other basis. So there are more sophisticated models where you actually try to learn the speaker factors or the weights that tells you what is the linear combination of the different bases for one system and synthesized system for the other situation. But we are not sure whether we have this problem in speaker recognition. So that is actually one of the things that we are considering to look at during the workshop. I don't know whether we will get that far, but one example that we thought of was if the speaker speaks different language. Isn't it something like that? If he speaks different language in training utterance and the other language in the other utterance, doesn't the speech really look so much different that we would need to synthesize completely different model that can be synthesized as a linear combination of some basis? So
finally, I want to talk about a project on multilingual spoken term detection, finding and testing new pronunciations. And one of the things that may not have been clear from Sanjeev's introduction was that a lot of these workshop projects end up being kind of a Frankenstein's monster, amalgamation of different projects, and this is certainly a good example of that. So Dream Team, yes. We're basically kind of a group of three project. One was on discovering new pronunciations from the web. The other was on what's commonly known as transliteration, that is transcription of the same word between scripts. And the third was on basically on some new techniques in automatic speech recognition. So what I'm going to try to do today is to argue that these are kind of related problems. Let me just give a brief point. I don't expect you to read any of this, but basically there's a simple point here, just a terminological issue. In the literature on, in particular on transcription between scripts, you'll often see the use of the term transliteration. I'm going to try to avoid using that term, although I will find myself probably slipping into it. And that is, technically speaking, the term transliteration actually means literally a system where it's basically a one-for-one map between the symbols in one writing system and the symbols in another. Okay, and that's actually really doesn't apply to most of the cases that we're going to be talking about. We're going to really be talking about transcription, and basically I'm going to try to stick to that term when I'm discussing the stuff we're going to be going over. Okay, let me start off with kind of a straightforward use of the term transcription, namely phonetic transcription from the web. Okay, and so here's basically the motivation, right? So, you know, if you think about how to get pronunciations for words, in particular pronunciations for difficult kinds of words like proper names and so forth, typically what people will do is they will create dictionaries. They'll get, you know, people who are trained to come and sort of do transcriptions of word pronunciations, and then use some set of rules which could either be crafted by hand, or they could be learned from these kind of data sources. Okay, now, you know, that's more or less expensive depending upon how much manual labor goes into it. Well, it turns out that these days a lot of the work is being done for us in a sense, namely that there are lots and lots of people out there, millions of people out there, who are providing pronunciations in various formats on the web. Okay. So there are, and these kind of range from really, really good to really, really iffy, okay? And furthermore, they also range in terms of sort of ease of extraction. So the easiest are cases like in Wikipedia, where people will actually use the International Phonetic Alphabet. It's sort of, it's coded in a fairly standard way. It's fairly clean. Of course, there's still no guarantee that the person actually knows IPA and knows how to use it correctly, but at least you know, there is some kind of vetting of the entries, so you can be reasonably sure that it's mostly okay. All the way down to what we'll call ad hoc pronunciations, and you see these in particular in a lot of English web pages. You've seen them on, you know, the New York Times does this, where they'll try to give a pronunciation of a word in terms of a spelling that they think is more intuitive than the original spelling. Okay, so that's the first part, and then the second is to actually provide some machine learning techniques for learning letter-to-sound models. We'll talk a little bit about that, and then finally to evaluate these letter-to-sound, to evaluate these pronunciations. Basically, we're going to talk about that a little bit at the end, but this is where this is going to tie in, you know, in particular with the speech recognition part. Okay. So here's some examples of IPA pronunciations. This is actually, I guess, from Wikipedia. So this is a pronunciation of the word Greenwich, which is actually not the way I say it, but in any case, it's this is the way this person says it, Greenwich, okay, of Greenwich Village. It's reasonably, as I mentioned before, it's reasonably easy to extract these kinds of cases. Wikipedia has a particular markup which is, you know, easy to detect. They tend to use fairly clean IPA for the most part. In addition to Wikipedia, there are also dictionary sites for lots of other languages that one can extract this kind of data from. Okay, so here's some examples of some extractions. Now, this number is old. We now have about 4 million, I believe, for. From the web, we have more. Okay, so I don't. Right. Okay, so I don't know how many you had from the web at this point, but in any case, we have 4 million IPA pronunciations. Okay, so here's some examples, and here's the pronunciation of the word Uruguay. Now notice this isn't entirely trivial because this is actually the phrase here was Uruguay River, but the thing that was extracted was actually Uruguay, just the first word. The other thing to notice is that depending upon the particular article that this is extracted from, the person may or may give a pronunciation which is not necessarily the pronunciation that an English speaker would typically use for this name. So a good example is the second one here, where this is a fairly good rendition of the pronunciation in, say, Hindi of that name, but it's unlikely that most English speakers would produce the aspirated B there. So this could be sort of taken as a starting point for extracting a pronunciation for English. Okay. Then there's general. Okay, so that was for Wikipedia and similar kinds of sources. Then there's more general IPA available on the web, and this is somewhat harder to extract for a number of reasons. First of all, you don't necessarily get the same clear, regular kind of markup that the Wikipedia enforces. Furthermore, people are, because these things are not vetted, right? I mean, they're just things that you find on web pages. You can't really be sure that the person even knows IPA. They don't necessarily use characters that are from the IPA part of the Unicode code space. They'll use anything that they think looks reasonable. So you have to be prepared to look for all kinds of crazy stuff. Okay, and so here's an example. Geisha, and then the pronunciation over here. Notice again, this is not adjacent to it. There's a kind of a clue here, the word pronounced, although obviously you don't necessarily want to assume that anything that occurs after pronounced is a pronunciation. Pronounced dead is a good example of where that wouldn't work. So what we do is we actually extract, we sort of limit the set of patterns. There may be more stuff out there, right, which will match this, which would be IPA, but we want to try to limit the set of patterns that we're looking for. So things basically within square brackets or slashes, and that contain one or more IPA Unicode code symbols. So basically, things that are we have some reason to believe at least the person is aiming at IPA. Okay, and then well, in the case of Wikipedia, again, it's a little more kind of restricted, but here we really want to make sure that the things that we're extracting, you've got a word over here or a set of words over here, and you've got a putative pronunciation here. You want to make sure that the stuff, something in the stuff over there, kind of aligns in a reasonable way with the stuff over there. This is a reasonable pronunciation of that. Okay, and so to do that, basically we train a simple finite state transducer to model the probability of the orthography given the pronunciation, and to come up with a score for the probability that this word, this pronunciation here is really a pronunciation of that word. Okay. Now this generally is going to give you pretty good precision, but obviously there's a lot of stuff we're not getting because it doesn't match this rather restricted set of patterns. Okay, so here's some examples. Now this is right. I guess this is really the number that should be updated here. This is the 4 million. So this was 50,000 when we did this, but this is now 4. Actually, we have 4 million of these things. Now this is actually not IPA in English, right? Yeah, no, in English.
Actually, your slide does say to be updated.
Yes, I know, and I'm giving you the update now, right? That's exactly what, in fact, what I am doing. This is obviously not IPA. This has been transcribed by these guys into Alphabet. Okay, now notice you get some, a certain amount of mess. So for some reason, on this particular website, this person thinks the word obliged is pronounced obliged, whether they really believe that or they just don't know how to use IPA, or maybe that's really the way they do say it, I don't know. But in any case, you get a certain amount of noise. Okay. Now, finally, there's these what we call ad hoc pronunciations. And these are things like, the boys and girls names Riley is pronounced Riley, okay, where this pronunciation, this spelling over here is supposed to convey the pronunciation somehow a little better, perhaps than the original spelling here, although in this case it seems kind of silly. So, yes, it does seem kind of silly. I think most people know how to pronounce that name, right? I don't know, you would know. Let's put it this way, that, huh?
Not many people say my name really.
Really? Oh, really? Okay. A lot of people can say my name's Sprout, but, you know, it follows regular.
I tried valiantly right now, just before you started saying it the right way. I know you gave me a rule. The rule is oats, and you have to then say sprout
Yeah,
the
maybe
way
you
you say oats.
I think you should remember goats, and then maybe it'll be easy.
Oh, goats!
Okay. So this becomes obviously more complicated because, well, you know, in this particular case, right, again, the word is there's no actual indication that this guy is really a pronunciation other than the fact that it's pronounced, you know, it follows the word is pronounced. Furthermore, it's not precisely because neither of these is a formal pronunciation representation like IPA, you've got to do a certain amount of work to sort of figure out whether this thing over here, which is putatively a pronunciation, matches that thing, which is the orthography. Okay? What we do is actually we have a simple regular expression that looks for things like pronounced as or pronounced like, followed by some stuff. And then we actually have two pronunciation models which are kind of composed together, okay, to give you a probability of this orthography, which is supposed to actually represent a pronunciation, matches that orthography, which is actually supposed to represent the regular spelling. Okay. Now, obviously, you know, this assumes some independence between these two. Okay, and basically, the idea is that this is actually going to be composed out of these two pieces here, the probability of this pronunciation, this orthography given that pronunciation, the probability of that pronunciation given that orthography, okay? And you basically sort of sum over all of the possible ways of combining them. Here's some examples. Now, for this, again, this says to be updated, okay? So I will now give you the update that we now have 5 million of these, okay? But these are just some examples that were collected earlier. So we have all of these words. Notice the word Alzheimer's or something, Alzheimer's or something like that. This person apparently pronounces the Z as it would be pronounced in German, although I don't think most Americans necessarily pronounce it that way. But in any case, and then there's some cases where, you know, it's, I mean, in this, I must say I'm not entirely sure in this case why this person thinks this spelling is any more transparent than that one. But in any case, you know, it's you get kind of a mixed bag of stuff. Okay, so one question that's interesting to ask is how well does this cover a list of names that you might get from somewhere? So one source of names is the US Census. And what this plot shows is okay, so let me sort of describe what we've got here. Along the x-axis here is the rank in terms of the frequency of the name as it occurs in the US, okay? So the things on the left are the most frequent names, and this is like binned by thousands or something like that. Basically, these are the least frequent names, these are the most frequent names. The plot here shows coverage of different sources. Okay. Now, let me just start with the blue line here. This is Pronlex, which is a well-known pronunciation lexicon. And as you can imagine, it has pretty good coverage of the most frequent names. That's what you would expect, right? Because it's, you know, it's a pronunciation resource that people have developed, so they want to make sure they cover the most frequent stuff fairly well. But it drops off fairly rapidly. Okay. Now, I want to stress that by coverage, I mean that we simply find the name in that lexicon. We do not know if that is in fact the correct pronunciation or the only pronunciation, and so on and so forth. Okay. Okay, what about some of these extraction methods? Well, you can look at the IPA. This is the combination of the IPA from the web and the more general web and the IPA from things like Wikipedia. And then the ad hoc pronunciations and the combination of those two. And what these show is that, well, not surprisingly, let's just say, for example, take the ad hoc pronunciations and notice, again, perhaps not surprising. Oh, by the way, I should mention that this is actually on the older count. So these numbers would probably shift up a little bit. These lines here would probably shift up a little bit with the larger set that we've collected, but we haven't redone the plots, I guess. But in any case, the basic idea then is that, not surprisingly, there's not so good coverage on the most common names, because you've kind of figured that most people probably know how to pronounce them. On the other hand, as you get further down, you start to see better coverage on these web resources than what you get for something like Pronlex. Okay, and when you combine all of them, Pronlex and all of these this data from the web, you get not surprisingly, the best coverage. Now, the thing to bear in mind is that, okay, it still drops down fairly low there. The point of this, of course, is not just to extract a static list, but also to derive pronunciation rules from this hopefully enlarged, improved set of pronunciations. So, basically, I've sort of removed the slide that goes into the details, but I'll just say sort of what we have in mind. So basically the idea is to take for training the pronunciation model is to take aligned words and their pronunciations to basically align the letters with the sound, so basically doing a string alignment between the two, okay? And then to build a language model over those pairs of symbols. So what the language model is going to give you is basically the probability of this grapheme will map to this phoneme given the previous n mappings. Okay, so it's going to be basically an n-gram model over pairs. Okay, and the idea will be to then evaluate that in various ways. One will be to sort of do a conventional evaluation on held-out data, and the other will be to evaluate it using the spoken term detection systems that the ASR group is going to be developing, and I'll say more about that later on. Okay, how am I doing for time here? 11:17. Okay. Okay, let me move to the second point, and just to be clear what we're talking about here. Here are some examples of what I'm going to be calling transcriptions, or what's more colloquially called transliterations. These are examples of the same word or name written in different scripts. Okay, so just for example, you have the word guru occurring in Cyrillic and in Kannada and in Tamil and so on and so forth. And all of these are extracted automatically from web resources. Okay. Okay. So just a quick note here. I don't know why the Language Tech Center decided to use the Rosetta Stone as its emblem, but other than the fact that the Rosetta Stone has become kind of emblematic for work on speech and language processing, I guess. But one thing to bear in mind is that this actually has a rather important role in the history of transcription, namely that it was names like this. This is the name Ptolemy. Okay, the Egyptians actually transcribed the names of the Greek rulers into hieroglyphic symbols, and this was it was actually transcription, or what's again more commonly called transliteration, that was enabled people to finally crack the Egyptian code. Okay, so this actually transliteration, transcription, whatever you want to call it, has a rather important role in history. Okay, so there's a couple of basic issues. Now we're looking not just, typically with the pronunciations, the web pronunciations, they're usually within, the cases we're looking at are within the same document, so you'll see a pronunciation given close to the word which is intended to be pronunciation of. In the case of transliteration, transcription, basically it could be that you find the transcription very close by within the same document, or it could be across documents. Okay, so you might be cases where you actually have parallel or comparable corpora where we have some reason to expect the same terms occur. So these would be language, in different languages, say English and Chinese, or English and Arabic, English and Hindi, whatever. And we expect there to be some terms that would co-occur, okay, and some of them would be transcribed from one script into the other, okay. Now, that brings up a whole bunch of other measures that one could use, in addition to presumably phonetic similarity, because in general, when people transcribe into a different script, they try to aim at something which is pronounced in a similar way, or at least as close as they can get. But there's also going to be other issues like graphical similarities. So there will be cases where people will actually sort of try to transcribe letter by letter. You do see cases like that. But there's also temporal similarity. I'll show you what I mean by that in a second. But basically, the idea is that if you look at a comparable corpus over time, you would expect terms that are related to one another to have a similar temporal distribution. Okay. So there's been a lot of previous work on this. I'm not going to go into this. The ones in red are some of the work that my colleagues and I have done at Illinois. So one of the measures that's clearly relevant is phonetics. It turns out that you can do very well even with a purely sort of knowledge-engineered, linguistically oriented kind of set of phonetic scores. So the basic idea is that you compare two phonetic strings, okay? And you want to say that certain kinds of mismatches are worse than others. So, for example, if you're talking about consonants, if you have a voicing difference between one language and the other, well, that's probably not as bad a mismatch as if you have a complete place of articulation difference. It's not, a T and a D. A T could be a transliteration of a D, okay, but, a T is less likely to be a transliteration of or a transcription of a P, okay? So we have a set of phonetic scores that are based on this kind of intuition. And we also threw into the pot some work on the kinds of errors that second language learners make when they're learning, in particular, English, because those kinds of errors or those kinds of mismatches also seem to be things that show up in transcription between scripts in many cases. Okay, for temporal correlation, if you take, say, I think this was 6 months of the Chinese and English gigaword, and you look at the distribution of terms like megawatty in English and Chinese, well, you see, a reasonable, not a perfect correlation, obviously, but a reasonably good correlation that when something happened in Indonesia that involved megawatty, you would see the terms would peak in both languages. Whereas if you say take two things which are presumably unrelated, namely megawatty and Arafat, then you will expect to find very little correlation. That's in fact what you do find. Now, obviously, this is going to be a weaker kind of correlation than phonetic similarity. Presumably, other things that have to do with Indonesia are going to also correlate in a similar way. Yes. Is that a person's name? Megawatty? Yeah.
Yeah. She's Sukarno's daughter.
I got it. It's not a...
I know what you're thinking. It's not that. Right. So I'm not going to go into the details here, but basically some of the previous work we've done, other people have done, is to show that if you combine these two sources of evidence, both phonetic and the temporal correlation, you can do better than either one alone. Okay, and in fact, depending upon how you do the combination, and that's something we plan to work on in the workshop, you can do substantially better than just using the phonetic distance. Okay. Okay, so briefly, the goals of the workshop for this portion are to set up some baselines, and we're kind of still working on that, although I'll report some initial results here. We want to replicate some of the previous improvements that we've had other people in the literature, also ourselves, have noted, and hopefully improve upon those improvements. Okay, and then the other thing we want to do is we want to look for other kinds of measures. There's been some interesting work, for example, by Haijo Lee and his colleagues in Singapore that have used phonetic confusions. You take a Mandarin speech recognizer and you recognize English with it, okay, and that gives you kind of a measure of the confusability between English and Mandarin. And since we have an ASR component to this project, one of the interesting things will be to see if we can use that kind of evidence as additional evidence for phonetic confusion. And at the end, we plan to make all of these tools available, and of course, all of the data available that we can make available at least. And the other point is we'd like to hopefully, in the case of the web transcriptions that I just talked about, it's kind of obvious these provide pronunciations for words that you may not have had pronunciations before. In the case of transcription, it's a little less clear, but hopefully we can also show that this is useful for ASR, for spoken term detection more generally. It's obviously useful for information extraction, but we'd like to show that it's also useful for spoken term detection. Okay, so let me just say a little bit about getting some of the data for the baseline. We have data from various sources, parallel data from the web, data from lexicons. For web mining, basically it's kind of a similar problem to the problem that I was talking about before with mining pronunciation transcriptions, basically looking for patterns, in this case where you have a string of text in some script, you have some kind of indicator like parentheses, and you have a string of text in some other script, because if it isn't in a different script, it's not interesting from this point of view, obviously. And then one of the tools we developed at Illinois was something we call Unitran, which basically allows you to take any UTF-8 or any Unicode code point and make a guess as to the pronunciation. Now, depending upon the script and the language, this is anywhere from quite reasonable to absolutely lousy, okay? Fortunately, for most of the world's writing systems, the phonetic to graphemic correspondence is fairly regular. So if I were to do this, for example, for say Kannada, Indian language, you would find that for the most part that if you guessed on the basis of the spelling, you do pretty well. Okay, and then we had some special tables for some other languages, Chinese for Japanese uses of kanji and so forth, and then we simply ranked by the untrained phonetic distance that I measured earlier. Oh, here's some statistics on the script. There seem to be an overwhelming number of examples of Latin and Cyrillic for reasons which aren't entirely clear. But here's a page of examples. Actually, the first one is junk, but everything else here is quite reasonable. Okay, second one is Georgian, for example, the Georgian rendition of that name. Okay, here's some examples from some Canadian Aboriginal languages, mostly Inuktitut. The point here is I just want to highlight one thing here, and that is relative to a point that I made earlier. This is all hypothetical, but if you take this pronunciation, which was actually derived from the Festival text-to-speech system's attempt to pronounce this word, it didn't do a particularly good job. It says something like poor look, okay, which is actually probably not how it's pronounced, and in fact you can get a clue as to how this is pronounced by looking at this and deducing the pronunciation from that. It's probably something more like poor look with a long U. Now, if you didn't know this word and you wanted to guess the pronunciation, this is an additional source of data. Okay. Obviously, it's much noisier than even the web transcriptions that we looked at before, but it is potentially useful. Okay, I think I'm going to skip over this. It just says that the automatic extraction produced, for the most part, pretty reasonable results, and that basically gives you an indication that the untrained phonetic distance that I talked about earlier is already doing pretty well. Okay. By the way, I should mention that in some of the work that we've done, you can take those phonetic scoring measures and train them using something like discriminative training and improve upon them. But the point is that you're already starting from a pretty good baseline if you just use the untrained measures. Okay, there's lots of corpora that are available. These are some of the corpora that we're looking at using. There's also one source of data for this kind of stuff is the set of names from the National Geospatial Intelligence Agency. They have about 4.3 million geographical names. Of those, there are about 300,000 names that actually have interesting scriptal variants. By interesting scriptal variants, I mean that you have it in, say, Roman script and some other script. So here's some example, for example, from Chinese. There's place names in Taiwan. Okay, we have some scripts that we put together to sort of extract potential. So in the case of parallel text, you basically since we don't know in principle, we're not assuming named entity recognition software, for example. We're simply looking for texts which we think are related to one another. They could be translations, they could just be comparable. And we're saying, okay, here's all the things that look like names on, say, the English side. Here's all the things that look like names on the Chinese side. Match them up and see which ones actually match well. Well, this is an example from the ISI Chinese parallel text. These are the cases where we are reasonably confident that they are actually parallel. And here's a bunch of words from the English side that look as if they could be names. Okay, here this actually happens to be the transcription of the word Maastricht. Okay, in Chinese. Okay. Okay. So the idea is one of the baseline evaluations done is the following. Basically, we take a bunch of randomly selected data from a bunch of different sources. So parallel corpora, the web, the National Geospatial Agency's sources. I kind of downweighted the Cyrillic, otherwise that would unfortunately swamp everything else. And then I went kind of hand-checked these 20,000 and came up with a list of about 17,000 transcriptions. And then the idea is to evaluate this. One thing you can do, right, is you can take, since we have this kind of as a gold standard, right, we can, 5 minutes? Okay. Really? I think you're cheating me by 5 minutes. Didn't I start at 11? Yeah, no, but didn't I start at 11?
No, you started at 11:10.
Oh, I'm sorry. Okay. Okay, so let me, okay, so I'll cut the arguments about this. I'll just say 5 minutes. Okay, fine, fair enough. Okay, so the idea is that we we have this kind of truth, right? And the idea is then we want to try to kind of bury those true transliterations in examples from lots of examples sort of randomly selected from the text and see how well we can sort of recover the true matches. And actually, let's skip over that. And here's the answer. Basically, for Arabic, you know, this we're only able to do this 0.92% of the time. And it turns out, I mean, basically, this is all based upon the fact that the pronunciation model that we're assuming, the pronunciation match model that we're assuming is far from perfect. And in fact, some of the things it thinks are better matches are kind of ludicrous. So there's obviously work to be done there. Okay, let me just, we're also developing a second evaluation set, but hopefully we'll be able to say more about that set. Okay, finally, I think I can go through this reasonably quickly. Okay? Good. Good, we're all happy. Okay, so I think I can go through this part reasonably quickly. This is the third part of the project, which is on basically evaluating the pronunciations in the context of automatic speech recognition in a spoken term detection system. Okay, so this is the basic problem for spoken term detection, right? You've got, you know, sources coming in, say TV, radio, news, whatever it is. You want to do some kind of a summarization, recognition and distillation, and you come out with a report. And hopefully that should mention the names and the organizations and maybe some things about what they're doing and so on and so forth. Now this kind of breaks down if you have lots of terms that are out of vocabulary. And unfortunately, the things that tend to be out of vocabulary are often the things that are of most interest, namely names and people, organizations, and so forth. You know, some new organization comes into the news, it has a funny name, and we don't know how to pronounce it, okay? There's obviously, you know, various ways in which you can get pronunciations, dictionaries, and so forth. Well, they're not going to be enough, obviously, because if it's new, then you are likely not to have it in the dictionary. But you can kind of try to extract from these dictionaries letter-to-sound rules. So far, so good. But then there are other sources besides dictionaries, right? There's also basically sort of more informal sources of the kind that we discussed already, namely people's attempts to give you pronunciations of words on the web. And there's also this kind of indirect use of transcription into different scripts, which could also potentially be useful. Okay, let me actually, well, so the basic idea here is the following. Okay, there's two ways in which we can kind of evaluate the contribution of these new pronunciations. One of them is kind of the most obvious way, right? Does that improve recognition on speech data where those names actually occur? Okay, so basically you've got a pronunciation for some organization. That occurs in that speech data. Hopefully, if you've got that pronunciation, it'll help you get that right. It'll help you find that one thing. Well, there's another way in which is maybe a little more interesting, kind of more novel idea, which is to say, well, okay, I don't actually necessarily know whether this is going to occur, okay, in my test data, my held out data. But let's see if adding those pronunciations for certain words based upon my pronunciation models actually improves the acoustic model that I would build if I were building this on this, say, this set of training data, okay? And, you know, we want to see whether or not that's actually going to improve the performance on held out data, whether or not those out of vocabulary words actually occur, okay? So, in other words, the pronunciations may actually be useful even if you don't actually find those words in the held out data. So that's the basic idea. Since I'm getting low on time, I think I'll skip the pie chart, which takes a little while to describe. And I'll just give you sort of, there's a whole bunch of the, you know, I don't want to sort of undertalk this portion of the project. The ASR group has been doing a lot of planning on this. They've planned a whole bunch of experiments. I just want to give you highlights of just two of them. One of them is kind of a baseline experiment, which is simply to you know, train some set of acoustic models and find a target word, an OOV word in some held out data, and to basically measure the likelihood of the acoustics given the pronunciation. So that's kind of a direct test of whether that pronunciation is reasonable for that word. As I said, the kind of the more interesting or more novel kind of issue is to say, well, okay, let's take a bunch of pronunciations, okay, that are proposed based on extracting this information from the web, from letter to sound rules, whatever, and let's assume that we have just pairs of pronunciations for simplicity's sake. For each pair, you can say, okay, well, let's suppose the pronunciation is this, okay? I'm going to train my acoustic model, okay, and it'll give me some acoustic model at the end of the day, okay? And then I can test that on held out data. Again, it doesn't matter whether the held out data contain the target words or not. The point is that if that acoustic model is benefiting from having that pronunciation in it, or as part of its training, then that should show up as an improvement in the when you compare this to the on held out data. Okay, and then you try the other pronunciation, and there's various ways you can measure this. You can look at things like phoneme error rate. You can look at the basically the likelihood of the two models under some kind of forced alignment. I guess sign statistic. The idea is how many times does each model perform better than the other, and you can do this for all basically 500 pairs. And the idea is that will give you an improved performance. So hopefully you can show improved performance based on certain pronunciations. That will give you a kind of direct feedback into whether those pronunciations are actually reasonable, whether the pronunciation modeling that you've produced is actually reasonable, and it'll also give you hopefully a way to improve ASR. Okay, so I guess, and then there's various ideas for doing this for multilingual testing. By the way, one of the issues obviously is when you look at other languages, especially, but even for English, there's all kinds of some of the most difficult cases are cases of, say, English words occurring, say, in a Turkish news source. Well, those are typically going to be pronounced in some sort of Turkified version of the English pronunciation, and can we use the set of different tools that we're developing during this workshop to help with that problem? Okay, I think I should stop now.